So this is a talk I gave a couple of weeks ago at Argonne called Out Loud. It is a talk that was designed to talk to the local community about climate issues that I work on. So it's kind of, there is no MPI in this. There are no cell counts or node counts, nothing like that. So bear with me. I hope it will be entertaining at least. So you heard that the whole day. Maybe it's good to escape from that. So the title of the talk is Navigating Changing Risk from Extreme Events. So when you want to navigate something, you really need to understand what you are trying to navigate. You need a map. So the purpose of this talk, originally designed, was trying to make some sense of the background of what an extreme event is, how extreme events are changing, and what role climate modeling plays in projecting how the extreme events will change in the future, and a little bit of work we do at Argonne on some of these things. So that's kind of the outline of the talk. So what are weather extremes? This is nowadays if you open a newspaper every day in the morning, there are at least 5 extreme weather events around the world, from fire in California to heat waves in Japan, which is kind of strange. I've never heard of Japan being so hot, but apparently it's a really, really hot place right now. And there is a picture of a lawn somewhere in UK that shows, like, the lawn is basically brown. UK, when you think of England, you think of green and all the stuff that you see in a lot of the rings kind of thing, but it's kind of all browned out. So because they haven't had precipitation in a while. So those are weather extremes that we are watching on TV and newspapers and all those places for a while right now. So what makes weather extreme, or what do we actually mean by an extreme? This is a picture from coastal flooding that's happened in Hurricane Sandy in New York City about 2013. It's an interesting event. So why did it become an extreme event? If this happened maybe a few hundred miles down the coast, nobody would have even cared. But when it came to New York, they're basically unprepared for this kind of event. Why are they unprepared for this kind of event? Because it's an extreme for New Yorkers. So New York never expected that they will get so much rain and that the tidal wave will be so much high and that they will get flooded. So because of that, rules were set up such a way that they can build houses and apartments without expecting that this kind of flooding could take place. That made an extreme event for them. But as I said, if it had happened about 500 miles, 300, 400 miles downstream, nobody would have even it would have been an event, but it wouldn't have caused so much damage as this one caused. This is one of the most expensive extreme events that happened in US in recent memory. So this actually has then led to a lot of investigations on how New York prepares for weather extremes, whether you should build a seawall at some point, and things like that. So there are a lot of discussion right now in both the government and in the private sector on how to face this kind of changes. This is another kind of event that took place actually very close to here. This also happened in last year actually. A whole bunch of towns around here got flooded because there is so much precipitation in just one event that nobody ever imagined that will take place in this place. So most of the drainage system, the sewage systems are all designed for 50-year events and 100-year events and things like that. This is something like a once in a 500-year event. Nobody expected that. So that became an extreme. So the precipitation essentially made this an extreme event for us. Again, if it happened somewhere else in the tropics, it would have been a different issue. Extreme heat, we are hearing a lot of extreme heat. So this happened again, I think about 2015. This is in Iran. This is in a coastal city around Iran, and the temperature reached 165 degrees Fahrenheit, which is a field-like temperature. And actually, this is not the highest temperature ever recorded. There is one from Saudi Arabia, which was 174 degrees Fahrenheit. So this is not the worst. You can get higher than this. This is actually an interesting thing. A lot of climate models now show that there are various portions of this earth, mostly in the Middle East, parts of Africa, and maybe parts of India, that most of the summer will be these kind of temperatures. So the word that is being used in literature is what parts of the world are going to be unlivable. So this is one of the things that has caught on. It's like this is going to be so hot. Basically you cannot work outside. You cannot perspire at this once you get into temperatures like this. And so the lot of productivity and all things will change. So this is Iran. And the more local event that happened here is in the 1980s. We had an extreme event here, like almost for about 10 days. We were about 90 degrees and above. That is the highest temperatures we see in summer. When you get them one after another, like 5 days, 10 days, it becomes an extreme event. So Chicago is not prepared for this kind of temperatures, and actually 750 people died that one event. So if this happened in Phoenix, Arizona, probably nobody would have cared. That's actually, if you look at the temperature around the same time in Phoenix, they were having 90 plus degrees Fahrenheit days over in Phoenix at the same time. Of course, nobody died there, but in Chicago it happened. So why is that? So it is, if you look at statistics, when you look at an extreme, the extremes are very specific to your local region. So that is the expectation you have of a climate in your region is actually being exceeded. It can be cold, hot, precipitation, whatever it is. So your life over a long range of climate events, we have a certain expectations of what we experience in a region. Once it exceeds over 95 percentile, you have seen it once in 100 years or 200 years or 1,000 years, then you get into this extreme event for that region. But the same thing, the statistic, somewhere else will not be a big deal. So that's the thing interesting thing to remember when you're talking about extremes. Weather extreme trends are changing around the world. This is an important thing to understand. This is not something. So when people talk about climate, you always think that is something at the end of the century, middle of the century, and things like that. But we are living through a climate change right now. I mean, this is happening every day, as you can see in the newspaper. So what is changing? If you look at the last 30 years, this is a map of flood magnitude, and frequency in the US from 1962 to 2011. So all the places where you see blue arrows are actually the frequency and intensity of flood has been increasing. This is just for the Midwest. Actually, if you look for the northeast corner of the US, it has been so freaking wet over a lot of the northeast over the last 30 years. If you look at the percentages, they are getting about 30% more precipitation over the northeast than they are used to experience. So what is happening with this floods is this intensity and duration of and the frequency of floods. As they go up, the local communities are trying to cope as they go along. I mean, it's basically seat of the pants kind of approach for a lot of the regions around here. In the Midwest, for Chicago, for example, they try to build a bigger storm drain to hold the water. Whenever the water increases, we get immense amount of precipitation. They are trying to take it out of the city and into the lake and into the river, things like that. So even the local communities here also are doing a lot of these things as things are changing. So one of the interesting things with climate is that as things change, we slowly adapt to this change. So we are constantly adapting to small changes. So when you think about it, 30 years ago, probably the people who are wearing certain kind of clothes who are in the Midwest probably don't need that anymore. So because the temperature has slowly changed a little bit. Same thing with precipitation. So climate is, as the last 30 years has been slowly changing, all the humans around the world are slowly adapting to this change without recognizing that it is not a delta change that one day it is 5 degrees warmer and then you notice it. It is small changes that are slowly happening. So that's one of the interesting things, and also one of the challenges for trying to convince people that climate is changing, because yeah, you have a small change. I talk to Defense Department people once in a while. One military guy told me, what's the big deal? I'll remove my shirt and wear a different clothing. So it's 5 degrees warmer. But at some point that you probably will have to work naked as you keep going. So that's a challenge here. So but maybe 50 years from now, we all will be naked and nobody cares. So, but that is adaptive. That is the adaptation path we are on. So we are doing small changes without realizing that we are actually adapting to these things. What actually is changing with the extreme events? There are three things that we actually try to figure out what are changing about extreme events. They are known as duration, frequency and intensity of precipitation. So these three define an extreme event. So that is, how long does the extreme event last, how often do they happen, and what is the frequency of them? Do they occur once every 5 years, 10 years, 100 years, or things like that? So how are these things changing as we go along in time? So this is a temperature chart from essentially for the last 40 years from India. And I chose this because this is one of the things that shows clear trend in changing temperature, frequency, and duration in temperatures. What happens when you change the duration is that a heat wave that lasts for 3 days now will be 4 days. A heat wave that is 95 degrees will be 98 degrees. So the intensity of the duration of the thing is increasing, and the duration is increasing, and the frequency is also changing. And the frequency is like you get a heat wave, maybe 2 heat waves in a summer, someplace like Southwest, most of the Southwest. Now they are getting 3 heat waves. The US Climate Service basically defines 3 days as a heat wave. If you get more than your 95 percentile temperature for 3 consecutive days, it is a heat wave. So now the heat waves are bunched together like you have a 6-day heat wave. So one of the interesting things is when you're doing statistics for the future using this current US definitions of heat waves, you actually count the same heat wave several times because none of them are 3 days long anymore. They are 10 days, 12 days longer. I'll show some of those figures there. So there has been a trend in these events all around the world, and the ones in this is the one in India that's a strong data set that shows that there has been a increasing trend. What is the current risk from weather events? So this is the cost of weather events, extreme weather events over the US. This is for last year, I think, yes, about $316 billion. Most of them happen because localized extreme events. It's not like one big hurricane came in and you lost, that's the cost of that. There have been events all around the country based on small scale extreme events that are going on. So each of this adds to the total cost of what the US government is basically paying. Some of this are covered by insurance. None of this is covered by insurance at this point, hardly anything. So the insurance industry is also trying to figure out, for example, you have housing stock in Florida. How would I insure that stock against changing in climate change? So they all operate. An insurance company operates based on an insurance risk table. The risk tables are prepared by a big company like Swiss Re or something, and they're based on data from the last 30 years. They have been fixed at that climate for the last 30 to 100 years for right now, but they can see that their costs are increasing. That means the risk tables are not relevant anymore. They need to somehow update them. So how do you update them? How do you do the projections of risk into the future? So that's one of the big challenges in actually trying to see the private sector actually plays a role in how we face the climate changes we are going on. So this shows the number of events that US has faced over the last 30 years. All the gray lines are for the past 30 years, and the ones in the colored are the last 5-6 years. So as you can see, each of them, each year it's going higher and higher. Again, this year is going to be one of the records in terms of how much change we are seeing in all of these costs and number of events. We don't have a hurricane yet, but there's so many events going on in the US. So there is a clear data that shows that the number of extreme events in the US has been increasing. So is there any other observation like real that you can see? So this is the one that shows changes in heavy precipitation. Heavy precipitation is defined as anything that is over your 90th percentile of precipitation. So if you look at the heavy precipitation for the last 30 years, again, this is from the US GCRP report, and climate, and it's called the NCA, National Climate Assessment, and they've done this. And you can see that almost all over US, you see an increase in precipitation. As I said in the beginning, if you look at the Northeast, the increase in heavy precipitation has been 71%. So they actually are seeing some of the heaviest increases in precipitation. Over Midwest, as I've shown before, the intensity of number of these events has been going up. So when you talk about this, we actually heavy extreme events, we always think about risk. What is the risk from a heavy event? So there are two things when you're trying to understand a risk. There is a hazard, which is a potential to cause risk, So if you have a lightning, there is a lightning hazard. If you are anybody from Chicago, we have a local meteorologist who has a nice application that alerts you if there is a lightning within a mile around you. So we get a email alert saying there's a lightning hazard close to where you are. So that's a hazard, right? Then, but what makes it into a risk? If it becomes a risk, if there is a property or a human or something else you value is actually exposed to that hazard. So that makes it into a risk. So every hazard is not a risk, and some of the hazards are a risk. If it is a lightning happening somewhere in the middle of the ocean, nobody cares, right? So that's pretty much it. So risk and uncertainty. So this again is an interesting set of ideas. Like you have complete ignorance, you don't know anything about anything, so you really cannot say the risk or uncertainty. Second, you can have uncertainty. So this is actually, I like this figure because it's not climate people and somebody economist doing it. This is from the British Federal Reserve, equivalent of British Federal Reserve, and they're trying to predict interest rates for the next 5 years. Of course, the models they use are nothing like the models you guys use or I use, but still they are models. They basically run Monte Carlo simulation trying to predict into the future. If you look at this table, that figure, the uncertainty is 0. It could be -1 essentially. It decrease in interest rate to a 4.5 increase in interest rate. But if you start doing a lot of these simulations, ensembles, that's where the big computers come in. Right now we cannot do a calculation like this with a climate model. Let's say I can run thousands of these simulations with a climate model. The middle part of that then becomes your uncertainty. Then that you have some confidence in the middle of the distribution that this is where I can trust myself a little bit. So that part of the uncertainty that you can define is actually the risk. So you need to understand uncertainty, risk, and as I said before, this is the key for this. If you want to see what is the risk from climate change or a hazard, you have weather events or climate events that actually feed into your risk, and physical, social, economic, and coping adaptive capacity. So recently there have been earthquakes in Japan and in South America. A 6.2 earthquake in South America caused massive destruction. The same thing in Japan did not cause so much destruction. Why? Because they have the adaptive capacity to this change. So let's say if climate changes, a foot of water increase in Bangladesh is going to be much worse than a foot of water increase in New York, because the adaptive capacity of this society is much bigger than somewhere else. So that's one of the things that plays into this thing. How capable is the society actually in coping with this risk, with this hazard that is coming in? So that's plays into the adaptive capacity. So when you're trying to model risk, you have to somehow calculate the adaptive capacity of a society, understand the adaptive capacity, and what are the kind of events that are causing this. So the third thing is exposure. What kind of infrastructure, population, and businesses are getting exposed to this risk? So if you think of Bangladesh, maybe the biggest thing that will get exposed are the people. If you look at New York, the biggest exposure you have probably are businesses. So this is again region specific. So one of the difficult or tricky tasks about trying to figure out what the risk from changing extreme events around the world is trying to figure out what is actually being exposed, either the people or how do you value that? How do you value a person in Bangladesh versus somebody else? So this has become a really a difficult and interesting problem as we go forward. And the next thing is the infrastructure. So not all infrastructure is the same. Like for Miami, right, for example, there are a lot of people having condos by this ocean. Apparently some of them are trying to sell and move up a little bit higher ground. So that is an infrastructure, but that is not critical infrastructure as the US government defines it. So US government thinks of critical infrastructure as something in Portland, Maine, where they have a lot of gas terminals and things like that supplies energy for most of the Northeast. So something happens in Portland, Maine port, then that is a critical infrastructure that is getting affected. So that has a much higher value in terms of where money will be invested in the future and what kind of adaptation strategies we'll be doing. So the goal of all these things is maybe one day you can come up with a chart like this as things change, what parts of the world are low risk, medium risk, and high risk. And then maybe we can direct resources to places where they are high risk or low risk, medium risk, as we go into the future. So how do we kind of model or project these kinds of risk as we go into the future? Of course, we all are mathematicians and love computers, so what we all first want to do is actually develop a forecast. How do you forecast these changes? And that's where climate models come in. So climates are trying to do these trends in extremes. So the other thing we need to do is actually move from a idea of weather to an idea of climate. The idea of the climate is that we are trying to predict trends in the 30, 60 to 90 years into the future. So you are doing long-term projections of climate change, and then obviously you are trying to model the climate, not the weather. So the difference between weather and climate, as this is a nice picture that everybody seems to like, but I don't really like it. But anyway, so weather is what you wear out for today because it's sunny, you're wearing these clothes, and the climate is what you have in the closet. That's kind of a neat way of telling you, I guess. I mean, closet, you fill your closet with winter clothes because you know the winter is going to be damn cold here. You have an umbrella if it is rains, and if you're living somewhere it never rains, probably you never have an umbrella in your closet. So things like that. I mean, do you have summer clothes? I mean, maybe if you live somewhere up in the Canadian north, you don't need shorts ever. I'm guessing. I'm not sure. I've never been there, but I guess there. So your closet does give you an idea of what you think the weather in your hometown is, or where you're living, and that is very important. So climate is basically what you got adapted to, or what your people living in Chicago got adapted to. Climate is what forces you to do agriculture in one place and not do in another place, because you have all the resources. Over the years, the soil is rich, the rainfall is nice, and everything is good, so you do agriculture there. Even if you buy a house, you actually make a decision based on climate, because when you're buying a house, you see whether you're buying in a floodplain or not. So you actually are looking at statistics, trying to understand, is it a place that gets flooded every 10 years, 20 years, 30 years, or things like that. So you actually, where you live, you actually decide based on climate. And where you farm, you decide on climate. And where you go on a vacation is also based on climate. You go to tropical regions because it's warm and nice there. Almost you're kind of guaranteed that that's what the weather is there. And that is, it is like that because that's a climate. And that's why there are coconut trees there, because it's been like that for hundreds of years, thousands of years. So that's what drives the climate there. So that's a kind of a way to understand the weather and climate, is that climate is basically a statistical average of what you're experiencing over a long time. In a practical sense, the definition of climate, when you see I'm seeing a change in climate, it's a 30-year average. So right now the epoch we use is 1960 to 1990. That's a 30-year average, and it moves to another 30 years as we go into the future. So some people use the last 100 years. So again, when you're looking at these charts, one of the things to understand is what is actually their baseline is. Is it the last 30 years or the last 100 years? So they look different based on those numbers. Of course, I had another slide. You guys probably wouldn't have liked it, but this is how do you do a climate forecast? I mean, we do develop an objective forecast. I really like this because long ago when I was learning modeling, one of the things is the first thing the professor who was teaching me said, imagine a square cow, which is actually probably what we do first thing. I mean, if you give us complex object, we try to simplify it to write something we can write an equation for. So that's our conceptual model of this thing. Now the idea behind that is that what I want to capture is the essential features of this thing. If I feed the cow a certain amount of grass, how does it digest? That's my question. So I really don't know the shape, don't care what the shape of the cow is, as long as I got the stomachs right and the enzymes right and things like that. So that's objective forecasting, and we use the same principle in climate change models, in the sense that Earth system, we idealize it. We idealize it in the sense that all the features are captured. Not every leaf of a tree is modeled. Does a leaf of a tree affect the climate? Probably, but not in the scale that we are thinking about here. So an aggregate of a tree. So if you look at a climate model, vegetation, a plant is actually it is a whole bunch of plants, like over 50 kilometer for 50 kilometer domain you have, that is all one single plant in the model. So it's a really big leaf, and things like that. So, but it does capture the essential features of what the trees do to the atmosphere and what trees do to the plant, water below, and how they transport water through the soil, how much greenhouse gases are they absorb, and things like that. Same thing with all the components shown here. The ocean. I come from a background in atmospheric chemistry, so the amount of chemicals in the atmosphere is again idealized. There are thousands of chemicals in the atmosphere. The ones in climate model are probably 10. Are they sufficient? Mostly. I mean, they do all the chemistry that you require to show most of the chemistry taking place in the atmosphere. The biggest thing happening in the atmosphere as a chemist is that there's a thing called oxidative property of the atmosphere. So how much hydroxyl do you have in the atmosphere? We call it a detergent in the atmosphere. So if you put a pollutant, that's the one that destroyed your pollutants. So one of the big questions in atmospheric chemistry is, are they going up or down? Is the oxidative capacity of the atmosphere increasing or decreasing? So those kinds of questions can be answered without a whole lot of chemistry, but you could do that. So of course, we put all those things, the initial condition problem, which is famous for any complex problem. It is fairly acute for climate weather models. Weather models are actually trying to forecast for the next 3 days, 18 hours. So they are very initial condition dependent. When you're doing a climate model, you're going to do the next 30 years, 60 years, and 50 years, and you're taking a statistical average. So it's not that important how your initial conditions are, as long as they are correct. You don't want to start a climate that is similar to Mars and hope that it comes Earth. So it is what we have. So most of the models start around 1850. So they start at 1850 and go for the next 150 years. So that's the way these are run. Mira is of course one of the big computers at Argonne. It has about 8,000 cores. I said I will not say cores, but yeah, that's my computing for now. So uncertainty is going from a known, the present, to future inevitable. The challenge is to define the extent of this uncertainty. So that is what a big computer for me will do. That is what advanced computing architectures that are coming online will help me, is actually define this uncertainty, and that's a challenge. It's not a challenge because you don't know what to do. It is a challenge because we cannot do it right now. The amount of resources we have are not sufficient. Again, I go back to this economist idea of uncertainty. Of course, those models again are Monte Carlo type and whatever. If you look at that and you look at the temperature forecast that is generated by a global mean temperature near-term projections related to 1965. So that's going up to 2050, and this is the historical thing. The black line is the observed temperatures, and all the wiggly black lines are what the models do in the past. And as you go into the future, the cone of uncertainty becomes bigger and bigger. And why does it become bigger and bigger? And one of the other thing to watch in that is that each of those colors actually represent a scenario in a climate model. I will just discuss what those are in a minute. But if you look at the blue lines, we kind of take as the uncertainty for a given scenario is what are all the spread in the blue lines or the red lines. So each scenario we can define an uncertainty cone, and that gives us some confidence on how we deal with this uncertainty as we go into the future. So the way to one uncertainty is actually doing initial condition uncertainty or even parametric uncertainty. That's one of the big things. The uncertainty in climate model is basically driven by parametric uncertainty. The uncertainty in weather models is driven by initial condition uncertainty. Both will benefit from doing ensembles. And this is a picture of an ensemble forecast that is actually used in some of the UK is trying to use this. So the idea is that if you look at a weather forecast today on your TV, it is actually one that deterministic forecast that is shown there with the dot there. So that's the only single forecast actually. So mostly we don't discuss the uncertainty over the deterministic forecast in any sense in a TV weather forecast or any other weather forecast that people share here. But in Europe, they are trying to say that using an ensemble they kind of forecast the projected possible range of temperatures for tomorrow. There is a 90% probability that your temperature could be 80 degrees or 70 degrees. So there is a range of possibilities, and there is a highly likelihood of something in the middle. So that requires that you every day you generate a whole bunch of these projections and start doing that. And the idea here is that the current climatology, the forecast uncertainty kind of fits into the current climatology. As the climatology keeps changing, your forecast uncertainty is actually beyond the boundaries of what we expect in this region. So that's where the uncertainty in extreme event is coming, because what your expectations are actually blown away by what is happening with the climate. So my way of thinking about role of climate modeling is, because I don't want to get into all the debate about greenhouse gases, good or bad for you, is I try this. Role of climate analysis is to study phenomena that results in shifting statistics. So basically think of that as that useful tool for you. All I'm trying to do is do a forecast into the future. How best can I do it? By doing that, can I build the statistics that actually help me figure these things out? So what are the statistics that are changing as you go into the future? One is, the easiest thing is shifted mean. You're going to have a higher temperature or a lower temperature to given, just the mean is shifting. So this is, you don't need a model for this. If you can kind of do with the fairly simple models. The second one is increased variability. This is the one that we are seeing right now, that the variability at the tails is actually increasing quite a bit. That's what is causing the extremes. So one of my friends call it the weirdness. The weirdness in the atmosphere is increasing, I guess. So that you can see that as the tails, the variability in the tails is increasing, you may get more cold weather. You could have deep cold snaps that we are having here, or you could have more hot weather and more record hot weather. So the hot weather is one thing, and then you get this highly extreme heat events. So the variability change is the second thing. And the third thing is changing in shape. So you may not have the same distribution of temperature. Most of the weather data, temperature, precipitation not so much. Other things kind of fall into this Gaussian shape distribution. So it's not unusual to see that shape in weather data. But as we go into the future, most of the projections are showing that we actually will change the shape of this thing. This brings us to the idea about non-transient in the atmosphere, so non-stationarity. So when I said the guys in Swiss Re are doing their insurance tables based on a fixed set of statistics, they are assuming that the climate is stationary. That the last 100 years is going to be the next 100 years. So that's an assumption of stationarity in there based on this thing. But most of the simulations, most of the things we are experiencing right now suggest that actually we are in a non-stationary state. So there is the considering non-stationarity in weather statistics and climate statistics is actually very important if you want to deal with these things in the future. So forecasting, again, I just like to think about this a little bit, so when you're trying to forecast into the future and building a climate model, it is not exactly the same thing as a weather forecast. As I said, weather forecast is driven a lot by initial conditions. Climate forecast, not so much. The biggest drivers in climate forecast are sun, of course, the three drivers: emission of greenhouse gases and large natural scale natural events like volcanic activity. So if you look at this, see, we have no control over it. Why are volcanic activities important? So if every time, like Mount Pinatubo in 1991, explosion actually cooled the Earth for about 5 years. What happens is when a massive volcano like that explodes, they put a lot of sulfur into the air, into the lower stratosphere, and that basically creates a veil over the entire Earth, and that cools the atmosphere a little bit. The signal from that could be observed for 5 years. So every time you see one of these massive volcanoes, we actually see an impact from that. And of course, we don't have any control over that. That's one thing. The second thing is sun. This is a solar sunspot activity from about 10,000 BC, I think. That's basically called the Holocene. That's when civilization started, I guess, and to current 2000 AD. The idea behind that curve is that the number of sunspots that are seen, of course they follow a cycle. There is a 11-year cycle in sunspot activity, but overall there is no large trend in the sunspot activity. So sun is not driving the current observed climate change. And the other cool thing right now is that there are so many nice models of the sun that are fairly good that you can actually reproduce the cold snap we had in 1740s in Europe, so-called the Little Ice Age from some of these sun models. So those models have been fairly good, and the expectation for the next 100 years from those models is that we are not going to see massive changes in the sun solar input on the Earth. So it's going to be somewhat, sun as a player in this is fairly small. There's large amount of confidence that this is not driving what we are observing right now. And of course the third, the biggest thing, the thing that we think is doing all these changes is emission greenhouse gases. But of course greenhouse gases are not easy to model, especially when you go into the future. So the uncertainty in all those scenarios that I showed before are basically driven by not knowing what the emissions in greenhouse gases are going to be in the future. So there are about the last IPCC report had 78 scenarios, I think, and because we don't have enough computing time, we only did 3 scenarios in most of the simulations. It will be ideal if you ran all the 78 with all the 40 models that are there to create a larger ensemble, but the ensemble size is limited because of the computing power that's available. So each of these things is a scenario. The scenario basically means that people build a storyline. So 2.6 stands for 2.6 watts per meter square heating by 2100. That means you imagine a 2.6 watt bulb in every meter square of the Earth by 2100. So 8.5 watts per meter square is that amount of heating that we're expecting per meter square by the end of the century. Once you do that, you can go back and calculate what kind of greenhouse gas emissions will take it to me. Will take that, will give you that scenario. So that's what the calculation is. So if you look at RCP 8.5, it's basically over 1000 ppm. Right now we are at 400 plus ppm of carbon dioxide in the atmosphere. The last time there was so much carbon dioxide in the atmosphere was about 3 million years ago, and there was no ice on the Arctic at the time, and the temperatures were 67 degrees Fahrenheit in the Arctic. So whether the temperature follows this or that is, I don't know that debate, but it's going to be different pretty soon there. So and RCP 8.5 is almost more than twice where we are right now. So just imagine that. So what does these scenarios mean? These scenarios mean that somebody built a storyline. The way I like to think about is that a storyline is you have to imagine how the society is going to evolve over the next 100 years. It's a pretty hard task because people are the most difficult to predict what they do the next day. Imagine trying to predict what they do 100 years from now. So the RCP 2.6, for example, assumes that it will be a very IT-based society where everybody stays home, works on their computers, and nobody going anywhere, no commuting, blah, blah, blah. I guess everybody weaves baskets or something like that to live. So that is the most ideal scenario that will get you to RCP 2.6. And also, one of the crazy things about the scenarios that are 4.5 and 2.6 is each of them assumes that there will be a technology that takes carbon dioxide out of the atmosphere. As of now, we have 0. So if you look at the Paris projections, that follows basically the 4.5 scenario. By 2030, they expect that there will be technologies that somehow take greenhouse gases from the atmosphere. I actually know of nothing that actually can do that right now on a commercial scale. So that's 15 years from now. So imagine that. So that's the most happy scenario if you think about it. So that somebody invents that. You can make a lot of money if you can invent something that takes out of carbon dioxide from the atmosphere. So that's RCP 4.5. So the idea is that people evolve. So predicting GDP for the next year is already difficult. You're trying to predict what the GDP is going to be 100 years from now. Essentially, how goods are produced, how much emissions takes place, what the power is produced. Some of these scenarios, for example, take into account that we'll be mostly using renewable energies. Some assume that there will be a mix of renewable and coal and nuclear, things like that. So all of them give rise to those scenarios, and each of them, that adds to your uncertainty. So if I follow one of these greenhouse gas emissions and run a model, that gives me some number. If I do the same thing with a different scenario, I get the different temperatures. So each of these things, the RCP 8.5 is about 4 to 6 degrees warmer by the end of the century. So the thing to keep in mind is that is the thing that drives uncertainty, but within each scenario there is fairly confident that once you tell me what the carbon dioxide is going to be at the end of 100 years, the spaghetti plot, even though it looks crazy, it's still manageable. It still tells you that this is, for this path we take, this is the uncertainty we have. But if you look at the whole thing, it looks like a crazy spread from -1 degree to 7 degrees, but that's not what it says. The way to understand that plot is actually looking at each scenario. That's why the lines are colored different in the one that I showed before. So again, I'd like to come back to this idea. So each of this color basically is one scenario. So you can see that the spread is there, but it is not as bad as the entire spread. So that's a way to understand this. Ensemble simulations are actually, if you can do more and more of them, and hundreds. Right now, the best you can do is maybe 20, 25 at best. Now imagine doing thousands of them. Then it will be, you can actually get into more handling the uncertainty in these models in the future. So what do we do at Argonne? So I just want to give a little bit of what we do at Argonne. So climate simulations, there is a global climate model called E3SM that Argonne develops most of the software for that. A guy named Rob Jacob at Argonne leads the computing aspects, software aspects of the model. And we also do agricultural crop models for this model, for this thing, and we also work on aerosols. And the second refinement of this is a regional scale model, which runs around 10 kilometers, a factor of 10 refinement, and the third one is local, that another factor of 10 refinement. So why do we need these different scales of outputs? Right now, if you want to get from global to regional at about the 10 kilometers, the only way you can do is something called dynamic downscaling. That is, you use a climate, something like a climate model, but over a limited domain, but driven at the boundaries from the results from a climate model. This is actually what most of the stuff I do, is this dynamic downscaling. So that is required because, let's say somebody wants to know what the impacts of climate change are going to be at a level that they can make decisions, and then they are mostly worried about what happens to my watershed or what happens to my drinking water here. So those are the kinds of questions people are trying to figure out, so that the thing to realize is that when somebody invests money in infrastructure, right now if somebody is wanting to build a dam, the lifetime of that is 50 years, and climate change is going to be real by the time. I mean, it's real right now. There may not be any water by 50 years if you don't plan for the changing climate. So a lot of the people who are investing in a lot of money from federal government, United Nations, giving money for dams around the world, they are actually trying to ask what will happen to this watershed, what will happen to the people living here. So those are the questions. They require very high resolution output. If you do this in 100 kilometers, then of course everything is smeared out and you cannot really see, can actually project changes in those scales they are interested in. As I said here, we have used the computers to develop the global models, and my focus is mostly on North America. We try to see what is happening over North America using the dynamic downscaling method I kind of described before. So what do we get when you run a model like this, a dynamic downscale model? So this shows for what we call CONUS, contiguous United States, I guess. It tells you, as you go into the future, these are different models, don't worry too much about that. But what you have to see is that if you see heat waves that exceed 95% historical level, 3-day heat waves, by the middle of the century, some of the west coast, western part of the US, there could be 18 of them in a year. So that is, again, problem is that you're counting 3 days as a heat wave, and then you keep counting, and some of these things actually last for a week or 10 days. So there's no point trying to count like this, but this is a statistic that is being used. So we almost need a new statistic to look at things like this in the future. So there could be 18 of those events in the future, and if you look at the end of the century, well, almost the whole country will experience lots of heat waves, more than a dozen, even in places in the Midwest, Chicago and things like that. We are expecting a lot more heat days. So one of the interesting things with working on climate is I'm working on this for about 20-25 years. So when we start some of the model output we saw early on, it looks like I don't know whether it's true or not. But for the last 30 years I learned not to be suspicious about climate model outputs. Everything that was models were saying 25 years, it's happening right now. So it's you have more faith in them. I actually have more faith in these things right now. So we also look at extremes in precipitation. So temperature and precipitation, the big difference is that precipitation is much harder to project or predict in a model, mainly because precipitation is stochastic. But we use a deterministic model to produce precipitation. So that creates one problem, and precipitation is also very spatially oriented. So if you cannot resolve the space very well, your precipitation is going to be average over a large domain, and you get, it's like putting rain in a bucket instead of a big tank. So you just smear the signal out, and you cannot get the real useful results. And most of the rain gauges, unfortunately, are on a location. So the precipitation they're measuring are location point based. So if you look at this figure in the 95th percentile, the models don't do that great, especially in the southwest and things like that. The bottom 4 are actually from global climate models. The global climate models are running at 100-kilometer resolution. The top ones are running around 10-kilometer resolution. So if you increase the resolution of the model, actually the models do a lot better than when you have a coarse resolution. So that's one of the big drivers for developing the new climate model, is actually trying to reduce the resolution of this model. So the model that DOE is right now funding, called E3SM, the final resolution is expected to be about 25 kilometers. So that's much more huge improvement over where we are right now, which is about 100 kilometers. The last IPCC report, the most common resolution of a climate model is about 100 kilometers. So they are coming to around 25 kilometers. Maybe in 3-4 years, a 25-kilometer model may be feasible. That will be, again, the big question is, you can run one simulation with a 25-kilometer model, but I want to run 100 of them. So how do we do that? So that's where some of the computing things we are discussing, you are discussing, will be useful. So the thing is, even in a very noisy, biased data set like that, the thing we try to look at is a trend, the common trend in all of them. So if you look at the green bars in those figures, they are precipitation greater than 95 percentile. Those are the intense precipitation. So almost all of them point higher. If you look at the black line, they are all also pointing higher. So that means the lower level of precipitation, the ones between 0, 10, 20% is going to decrease in the future. The ones that you get a short burst of rainfall, which is in your 95th percentile in the future, will actually increase. So that's the way the statistic is going to change as we go into the future. And we also try to do tracking rainstorms and time and size. So this is one of the things that I think machine learning and advanced computing techniques would come into play. Here we try to follow a storm, this is in a model, by coloring it by blue or something like that. So what happens is, when you have a storm event in a model or real life, these cells combine together, break up and spread around, and they are all over the place. But still, you know, they are all from the same storm. So you need to have a technique that actually follows that storm, and the cells break up, but you still keep count of the same storm and not count it as a different storm. So this is a technique that my colleague Juan Cheng, who's from University of Chicago, and right now at Connecticut, I think, he developed it, and the idea is to follow this time step by time step and still count of the same thing. The advantage of doing this is, well, the question we ask is, why is the intensity of the precipitation changing as we go into the future? What is driving it? One of the conclusions of this paper is that the size of the storm as you go into the future is becoming smaller. If you look at the climate data model output, so they're becoming smaller, and you're getting precipitation over a smaller area, so your intensity of precipitation is increasing. So why is the next question is, why is the storm becoming smaller? I don't know the answer. People are trying to figure out why the storm size is actually decreasing in the future. If you look at the model output, if you look at real data right now, this is what is going on. The storms are becoming smaller, and the precipitation is increasing. And these kinds of techniques, the output we created is about 700 terabytes. So this guy ran through that whole 700 terabytes of data, kind of. But we still left a lot of data we couldn't use, because it's not fast enough to do all the stuff we want to do. But one of the challenges is that when you start having data sets like this, 700 terabytes or whatever, and I know I have a specific problem. Either how can I follow a storm track or a cell of a storm that I can still keep count as it changes. There are probably 10 different storms happening over the United States at this time, but each one is a single storm. But after a while, each storm will split up into a number of cells. So by an hour or 2 hours after a storm, you may be having, from each storm's event, you may have 10 cells. So it kind of multiplies as you go around, but you still want to keep count of it. So that's the challenge here. The model we run saves data every 3 hours. So I have 3-hour time steps. Let's say next thing we want to do is run these models at a resolution of 4 kilometers. At 4 kilometers, we say we actually resolve the convective process in the model, so we don't have to parameterize, and then the data will be saved every hour. So if I do that, of course the data is going to be in petabytes. So, but then you can follow these cells maybe better, because every 3 hours if you see them, you probably have a bigger challenge than every 1 hour if you see them. But those are the kinds of things we are trying to find out how we can do as we go into the future. As I said, we also help, this is Department of Homeland Security and the Portland example I gave you, trying to figure out what the risk to infrastructure in the port of Portland, Maine is. We try to use the precipitation for the future, changes in the precipitation, changes in temperature and sea level rise and things like that, to predict what is happening along the coast of along the port of Maine, and what infrastructure may be at risk from 50 years from now, 30 years from now, 100 years from now. So these are the kinds of things that people are really interested right now, trying to make decisions. And anybody who's making an investment 30, 40 years from now is actually worried about this. And we work like this. We work with social scientists, climate scientists, risk analysts, and try to, one of the key things in this kind of discussion is that what we call a stakeholder. A stakeholder is a person who's interested in knowing what is going on. For example, if you talk to City of Miami, anybody who runs the city government of Miami is a stakeholder for us. So discussing with them what actually of interest to them is very interesting, because they generally are not interested in a lot of the stuff I'm interested in, and the stuff they are interested in I'm not interested in. But the idea is we both work together, at least on this graph I can show that we all work together, and the word that is used is co-production of model output. This is actually the biggest challenge for climate modeling. Actually, how do you transfer all the things we are doing to somebody who can actually use it? And the word that gets thrown around is the co-production of model output. So before I run the model, I actually talk to these people and understand what they want, and then I put the right kind of output in my output. Then maybe we can work together and try to figure this out. So that's actually the massive biggest challenge we have right now. Each stakeholder is different. If somebody is, if you go to the West Coast, the guys, the power industry and the people running the utilities are actually interested in fire. That's all they care. I mean, what can we do about fire? What can we do? Can we calculate some kind of risk in the future for fire? So for fire is not a model output, but you can do things that actually create fire. So, but sometimes I don't save them. But if you talk to them, then you know what kind of variables going to do doing those parameters. So that's the kind of thing. For a drought example, drought is not a model output; it is a derived output. So if somebody is interested in drought, what should I save? So this is the co-production challenge, and one of the biggest challenges is that once you run the model, as I said, the simulation that produces 700 terabytes took 100+ million hours on some of the big computers here. So I took 3 years. There's no way I can go back and do that whole thing again. Once you're done it, then you're done. So that's a problem. So the 4-kilometer thing, we are trying to talk as many people in the stakeholder community as possible to create this so that it's useful to as many people as we can. So that's it. Thank you.